are expected to know what I have covered under stability. Okay. One of the important things to start with is the stability is the Can you see me? Can you see the whiteboard clearly? Yes, class? Those who are joining online. You see? Are you able to see? Yes, okay. Now, the first thing that you are expected to know is the concept. Yeah? What is stability all about? So the first thing that I cover is understanding the concept. So how you will explain the concept of stability that we have, which is to explain the state of equilibrium. So you know this, but you should be clear now how to explain stable, neutral, unstable. Okay. So this is the concept of stability. What is stable, what is neutral, what is unstable. So it has to be always related to what happened after you disturb it, and the disturbance disappears, it goes back or not to the equilibrium state, it stays where you disturb it, or it goes away to far away. So those are the first thing that you should be aware of, the concept. So you can use the concept using the ball concept, or you're using the, so this is always the concept that we use. This is stable, this is neutral, and this is unstable. So that is the diagram that we commonly use to explain, but you can, if you're asked to explain using a column, then you can use the column to explain, namely when the column is subjected to P less than P critical, P more than P critical, or P the same as P critical. So if we are using the column, so it will be, let's say I use this, so this will be the state P less than P critical. The second one will be P exactly equal to P critical. And the last one is when P is more than P critical. Okay. So this one will always, if you disturb it, it will move here and there, but finally it goes back to the original state. This one, if you disturb it, it will stay there on the equilibrium state, which is next to the, which is slightly disturbed state. And the last one, it will not go back to this equilibrium state, but instead it will go further away from the equilibrium state. Okay. So this one is the first thing that I covered. This is on how to explain the concept of stability. Okay. Now the rest of the lectures that I cover talks mainly a lot about methods. Okay. Methods to determine P critical. Okay. So we cover methods of neutral equilibrium. Okay. And then we other methods, we use slope deflection equation, and we use the another one is the matrix method. And one method which is also we use, which is the energy method or Rayleigh-Ritz method. So these are mainly the coverage is on these four main methods. Okay, we start off with method of neutral equilibrium. We make use of the concept of neutral equilibrium, which is at the P critical load, two equilibrium positions are possible, and then we find the P critical that will give you the non-trivial solutions. That is method of neutral equilibrium. This one you have to derive using, you have to derive the partial, you have to derive the differential equations. Okay. Slope deflection equations, you are given the slope deflection equations that you need to make use of. Then you have to form equilibrium equation of the joint where the rotation is non-zero. Then you solve for the non-trivial solutions. And then finally, from there, you get the P critical. Okay. The matrix method, you will be given the stiffness matrix that you need to use, and then you need to form the structure stiffness matrix, and from there you use the methods conditions that in order to get P critical, then in order to get non-trivial solution, the determinant of the structure stiffness matrix must be zero. So this is the overall first. Later I go into a bit more detail. Rayleigh-Ritz method, this is similar to 661, except that you use this to determine P critical. So you have to calculate the strain energy due to bending, then the potential energy due to the axial force. Then from there, you apply the principle of stationary potential energy. From there, you get one equation, then you solve for the P critical using Rayleigh-Ritz method. Okay. Now, before I go a little bit deeper into this, we also cover the concept of this neutral equilibrium is for perfect column. This is for perfect column where if you talk about a column, it will stay straight. It will stay straight, yeah, before P critical. Then at the point where P is equal to P critical, it can stay in this slightly deformed state. Okay, it can stay in this slightly deformed state. Then that means you have a possible two solutions. If it is above P critical, then the straight one is not stable anymore. It has to go to the unstable state. So this neutral equilibrium concept is for perfect column. Then we also touch about the imperfect column. And there are two sources of imperfection. The first one is the geometry, which means it is slightly bent right from the beginning. The other one with eccentricity in loading. And we look at how the perfect column and imperfect column, their behaviors are different. In imperfect column, right from the beginning, you have bending. And as long as the P is lower than the P critical, very much lower, you don't have, the bending will become less. But as soon as the P approaching P critical, you have a very large change in deflections, which is you have this delta and then P over P critical, then you will have this kind of curve, which is imperfect. Depending on the level of imperfection, then you have, this is for different level of imperfections. The higher the imperfections, the maximum load that the column can take will be less. Okay, the smaller the imperfections, then it can get very close to the P critical. And for eccentricity in loading, you get very similar types of a curve. Okay. Except for eccentricity in loading, the curves start from zero because there is no initial crookedness because the column is straight, but only you have eccentricity in loading. So similar curve, but only the curve start from zero. Okay. This one does not start from zero because in the beginning, when there is no load, the column already bent. So we touch also on that perfect column, imperfect column, which is to know what is the difference. So you must know what is the difference between the behavior of perfect column and imperfect column. Okay. So perfect column, the behavior, if you want to plot, it will be here. The perfect column will be here. Perfect column is everything perfect. There's no deflections. So when it comes here, there's a bifurcation point, and it can go to another solution. And if you go up here, then the straight one become unstable. So this curve here, this is for perfect column. And imperfect one, immediately you apply loading, immediately the P is non-zero, you get bending. Okay. So that is also one thing that I cover, and you expected to know what is the difference between the behavior of perfect and imperfect column. And of course, finally, we in the beginning part, we talked mainly about column, and also in the final part, I touched also on buckling of frame. Okay. So buckling of frame mainly we cover just not too much. Buckling of frame mainly we would like to know if you have symmetric buckling, which is the frame is braced, what is the possible range of P critical? And if we have non-symmetric, asymmetric buckling, which is not braced, so we use the example of this. If it is braced, okay, means it's not allowed to sway. This is no sway or brace. And if we have another one which is sway is allowed, so we don't brace it, and sway is allowed. So you permit the sway, okay? So this is unbraced. So when we talk about buckling of frame, so you have this, if you have a loading applied here. So what happened to the frame when the load is equal to P critical? So what will be the buckling mode? Okay. What will be the lowest buckling possible mode for each case? And if you need to estimate what is the range, so what will be the possible range where this unbraced one, the P critical is always lower than the braced one because this is allowed to sway. Okay. So we talk about the lowest possible buckling mode shape. This is symmetric, so it is going to go like this. So it bends into this shape, which gives you the lowest possible buckling mode. And for this, it's not allowed to sway. That's why this and this, there is no lateral translation. This point and this point, they are not allowed to translate. But here, when it is allowed to translate, then you are going to get so this will be the corresponding buckling mode shape for frame if we talk about whether it is sway or no sway. Okay. Then the buckling load here will always be smaller than this buckling load because the restraint that we have. Here, we take, for example, this is the same restraint, but if the top one you're allowed to sway, then P critical will be, of course, lower than this, and we can estimate the range. So that is the main thing that I cover. So I give you an overall view first. Okay. Any question so far before I go into more detail of it?